Hello, so in this video we're going to be looking more about forces, in particular how we can relate forces to acceleration. Okay, so before we actually jump in, one thing we need to look at is weight. Okay, so previously I discussed, let's say I have some object, what's going to be always pulling it down is its weight. Okay. Obviously, against that, there will be a reaction force that stops it from just sinking down the ground, right? So, for example, if you're on a chair, you don't just sink through the chair, right? There's something keeping you on the chair. But the weight is the force that pulls you downwards, okay? And so weight, you need to know that we can actually compute the weight by, so if the object has mass, right, it's mass times g, okay, because it's to do with gravity, right? So this g, if you remember, it's so if we have a ball that falls down, the acceleration we said is 9.8, right, meters per second. We looked at that in the last chapter. That's g. Okay, so usually g is 9.8. Okay, or they might say it's 10 or something like that, but usually we say that this acceleration, because of gravity, so things going down, is this g 9.8. So it's just a number. So weight is the mass times this acceleration gravity number. Okay. And so most of the time what we'll be doing is to compute the weight, we times the mass by 9.8, okay? But the important distinction here is the mass is how much you weigh, so to speak. So, for example, the number on a scale, that's your mass, not your weight, okay? Unfortunately, in real life, we use weight incorrectly to reference the number on the scale. It's your mass. The weight is the force that pulls you down due to your gravity and your mass. Okay, so weight is the gravitational force pulling you downwards. Okay, and we need to be able to compute the weight. Okay, by doing mass times this number g, which is usually 9.8. Okay, right. With that out the way, we last time I said a few videos ago I spoke about Newton's first law. So remember, the first law states if you're travelling at constant velocity, the forces must be balanced on the object. Okay, and that's the first law. The second law we're going to look at in this video is basically can be summarised by a formula. Okay, it's F equals ma, and you might have seen this before, maybe at GCSE, maybe you've heard of it. And so what this is saying is F is a resultant force. So we looked at computing a resultant force previously. The overall force. M is your mass, and A is your acceleration. Okay, so what this does is links the force, the mass and the acceleration of something together in this one nice formula here. Now this is quite substantial, might not seem it, but mechanics looks at, in this course anyway, it looks at overall two topics. It looks at forces and motion. This formula links both those together, so it creates a gateway between forces and motion, because obviously F is your force, the acceleration is to do with motion, how the particle moves. Okay, so it's quite a significant sort of result, but we will be using this a lot throughout the course, and we're going to start it now. So this is your second law we'll be using throughout the video and beyond. But yeah, so these two formulas here you need to be aware of. You're not given them in the formula book, but honestly you will remember them once you do a lot of examples. Okay, so we're going to just apply this then to see what this actually means with this example here. So this example first, we want to find the acceleration of a particle of mass 1.5 kilograms acted on by a resultant force of 6. Well, very simply, we just use the formula. So F equals ma. Okay, well, we've got the mass of 1.5, the resultant of 6 newtons. So we can say 6 for the force is 1.5 for the mass times the acceleration. So how can we get the acceleration here? We can just divide by 1.5, right? So 6 over 1.5. If we work that out, we get 4. So that'd be 4 meters per second there. Okay. And so there we are. Okay. Now let's look at a kind of example where you actually apply it. So you apply the formula in a sort of physical situation. Okay, so we've got these force diagrams. So the diagram showing all the forces acting on an object. We need to work out the forces X and Y. Okay, so we've got X and Y here and here. So we need to find them. Okay, so we're also told, as well as the forces, if you pay attention up here, we're told the acceleration and where it's accelerating to. Okay, so it's going forwards. Okay, so what we're going to do, again, we're going to use F equals ma. But how exactly do we use it here, right? So as I discussed, F is the resultant force, A is the acceleration, and M is the mass. Okay, now this resultant force F. Okay, well, we know the acceleration is 2 forwards. Okay, that's the direction, it's going to the right. Okay, so that means if you remember the last few videos, we discussed resolving. So what we're going to do is resolve forwards. Okay, so to the right. This is resolving horizontally. So what we're going to do is look at the right force first. Well, it's X. The force going to the right is X. Then I'm going to take away the forces to the left, so the opposite side. So that's going to be 4. So X minus 4 has to equal mass. That's the resultant force, right? And so in this case, this is the resultant force. So that has to equal, because it's accelerating forwards, it's going to be the mass. The mass is 2 here, 2 kilograms, times the acceleration of 2. So if we work that out, we're going to get X minus 4 is 4. So then at that point, we just add 4 to get X is 8. Okay. Now, we're also going to consider the vertical forces. So that was horizontal, so right and left. Now we're going to consider the up and down forces. So if we resolve upwards then, so firstly, the up force is again Y. Take away the downwards force, the opposite, which is 2G. So Y minus 2G. Now, what's that going to equal to? So that's the resultant. So that's the up force, take away the downward force. Now, the acceleration is only going to the right. Okay, it's going horizontally. The acceleration is horizontal. There is no acceleration upwards. Okay, which means, well, there's no acceleration upwards. So if we did mass times acceleration, so ma, well, the mass is again 2, but the acceleration upwards is 0. Okay, so I want to emphasize that this is horizontal acceleration. It's going to the right. So there is no upwards acceleration going vertically. Okay, so the vertical acceleration is 0. Okay, so that means we can equate y minus 2g to equal 0, so y is equal to 2g. If you were to work that out as a number, remember g we take to be 9.8 unless told otherwise. So y is 2 times 9.8, which is 19.6 newtons. Okay, and there we are. Okay, so that is again the idea. We'll be applying this. We'll be looking at the forces horizontally and vertically and applying this formula here. Okay, let's have a look at part B. So the first thing, well, we've got these forces again on here. The other thing to note is the acceleration is going to the left. Okay, that's the arrow. Okay, so the arrow is telling me the arrowhead is to the left, so the acceleration is to the left. Anyway, so if we resolve to the left, then firstly we can resolve to the left. If we do that, So the left force first, which is 80. Take away the right force of X. Okay, so I'm doing the opposites. So that's the resultant force to the left. Okay, so again I did the left force, take away the right force. That's the overall horizontal force. Okay, now that's going to equal mass times acceleration. The acceleration is to the left, so it's going to be the mass of 4 times the acceleration of 2. Okay, if we do that, if we solve this, then we get 80 minus x is 8. So then x is going to be 72 newtons. Okay. Alternatively, you could do the other way, and instead of going to the left, we could consider going to the right. So if we resolve to the right, so then we start with the right force. In this case, is x. Then we take away the left force instead, so that'd be 80. Then again, that's going to equal mass times acceleration, where the mass is again 4 times the acceleration. Now, because we're going to the right, because obviously that's where the arrow is here. The arrow we're starting with the right side, the right direction. The acceleration is going the opposite way. It's not going to the right, it's going to the left. So we will have to make it negative. Okay, so instead of 2, it's going to be minus 2, because it's the opposite way. If we're trying to go to the right here, that then going to the left is the other direction, so it's negative. Okay, so if we solve this equation instead, we'll get 8. X minus 80 is 4 times minus 2, that's minus 8. So x will be 80 minus 8, which is 72. So we get the same answer. Okay, so you can go in whatever direction you want. You can go right or left, but do pay attention to making sure you consider where the acceleration is going. Okay, so if it's going opposite to where you want to resolve, so if you want to start with the right direction rather than the left direction, you need to pay attention to the sign of your acceleration. Right, so that's horizontally, so that's right and left. Now we're also going to resolve upwards. Again, the acceleration is only going horizontally, so left and right. There is no vertical acceleration, only horizontal acceleration. So that means, well, the upwards force is y. That's the only force going up. Take away the downward forces. Well, actually here we've got 2 downward forces. We've got our 4g, right? So take away 4g. And we've also got this other downward force here, 20 newtons, but it's going down. Okay, that's where the arrow's going. So we're going to take away a 20 as well. So, okay. So I did the upward forces, take away the downward forces. And again, the mass is 4, but there's no acceleration. So ultimately this equals 0. Okay, because there's no vertical acceleration, only horizontal. Okay, so if we solve this, then we get y equals to 4g at 20. Then if g equals 9.8, then y is going to be 4 lots of 9.8 at 20, which is 59.2 newtons, and there we are. Okay, so that's that. Okay, so we've got this question here, which is a bit harder. You need to kind of construct the diagram yourself here. But here we're told a body, so an object basically, of mass 5 kilograms is pulled along a rough horizontal table by a horizontal force of 20 newtons against a constant friction force of magnitude 4 newtons. Okay, so again, if we draw this diagram out, firstly it's a horizontal table, so horizontal, so it's going to be like that. We have our body, so I'm just going to draw this little box here to represent it. And the mass is 5, so I'll make a note of that, 5 kilograms here. Right, now in terms of forces, we're told that there's a horizontal force that pulls it along. Okay, so it's pulled along by this force of 20, so it's going to be pulled forward in that way, and that force is 20 newtons. okay? And it's against a friction force of 4. So the friction the opposite way will be 4 newtons, okay? There will also be weight that pulls it down. Now again, weight is mass times G, okay? This G number. So the mass is 5, so it's going to be 5 times G, or 5G. That's the weight that pulls it down. What will pull it up, what keeps it up, is going to be a reaction force I'll call R, okay? And that's all the forces. Now, what we're told, we're also told it's initially at rest. Well, first of all, there's going to be acceleration, right? There will be acceleration as it moves forward. So acceleration forwards, and we're told it's initially at rest. So there's also an initial speed of 0, right? In that way. And we're told, firstly, to find the acceleration, okay? Now, okay, the acceleration, first of all. So hopefully you're with me with that diagram there. Hopefully that made sense. So, what we're going to do, well, if we use F equals ma, right, we're going to be using that. But we need the resultant force. F is the resultant force. So what we're going to do is we're going to look at the horizontally. That's where the acceleration is. The acceleration is going to the right, okay? So if we resolve to the right, so this is resolving vertically, remember? And the horizontally, sorry. So right and left, right? So if we start with the right, well, the right force is 20, that's moving it forward. Take away 4 newtons, that's the other way. So take away 4. So that's the resultant force, right? That's the right to take away the left force. That has to equal mass, which is 5, times the acceleration. We don't know what the acceleration is. I'll just call it A. So 5 times A, okay? So we get this equation here. So that means 16 equals 5A. And so therefore, to get A, we just divide by 5. And so if we work that out, we get 3.2 meters per second. And I can add that on. So that's my acceleration, okay? So that's how we'll be working things out. Right, then in part B, they want the distance travelled in the first 4 seconds. So, as we said, initially the speed is 0. Now, what we're told is, if we extend it, after 4 seconds it moves along the surface, right? So when the time is 4 seconds, obviously it's going to have travelled, if it started here, and end all the way somewhere here after 4 seconds, that's my distance, right? What is my distance going to be? So how far has it travelled after 4 seconds? That's what I want to work out. That's going to involve Suvat, right? That's going to involve Suvat. So S is the distance. That's what I want to work out. U, well, the initial speed is 0. V, I don't know the final speed after 4 seconds. I don't really care. The acceleration we just worked out. The acceleration is 3.2. And T, the time, is 4. So actually, I need the formula that does not involve V from these Suvat equations. Well, it's this one here, right? S is UT, add a half AT squared. Okay, so S is going to be 0, add a half of 3.2 times 4 squared. And that will be, if I work that out, 25.6 meters. So after 4 seconds, the distance is 25.6 meters. Okay, then it says in part C to work out the magnitude of the normal reaction between the object and the table. Well, it's this reaction force here, as we discussed, right? Here. So again, this reaction force kind of opposes the weight that pulls it downwards. The reaction acts perpendicular, so right angle to the table, and it pulls it forward, so it stops the object from just sinking through the table, right? Like how you sit on the chair in the classroom, you don't just all sink through the chairs, right? So there's a reaction force keeping you up on the table. So what is this reaction force? Well, these are the vertical forces, right? So if we resolve vertically, so if I resolve upwards, so now we're what we call resolving vertically here. So last time we looked at in part A, we were resolving horizontally. Now we're going to resolve upwards, so vertically. Now the vertical force upwards is R. Take away the downwards force, so the opposite direction of 5g. That's my weight. Take away 5g. Now that's going to again equal mass times acceleration. This overall force equals mass times acceleration. Well, the mass is 5 times the acceleration. Now the acceleration is not 3.2. Okay, what you need to pay attention to here, as we discussed, is the acceleration is horizontal. It's moving to the right. The acceleration is acting to the right. It's a horizontal acceleration. Okay, I'll make a note of that again here. Horizontal. But we're looking vertically, so up and down. There is no acceleration vertically. So that means the acceleration vertically, because we're resolving vertically here, is nothing. So simply r minus 5g is nothing. So r is equal to 5g, which is 5 times 9.8, which is 49. Okay, 49 newtons. And what you and then what a lot of the time what happens is the reaction force would actually equal the weight. So 5g on the top and the bottom here, they have to be equal to balance each other out in here, in this case, so you don't just fall down or above or float up. So you don't fall down the table and you don't like float up in the air. So they kind of have to be balanced in that way. So the reaction force equals the weight here, okay, as we just seen. And so that's the main thing to pay attention to, is the acceleration. Where is it going? So if it's moving to the right, then obviously that's horizontally, but vertically there's no acceleration. There we are. So that's the reaction, okay. It equals 5g or 49 newtons there. Okay, let's have a look at some exercise questions. Okay, so this one's quite an interesting question. So here we're told an astronaut weighs 735 newtons on the Earth and 120 newtons on the Moon. Work out the value of acceleration due to gravity on the Moon. Okay, now I said this here. If you're not on Earth, the gravitational constant g, so the acceleration because of gravity, isn't 9.8 necessarily. Now, we're told here it weighs 735 newtons on the Earth. So if we was to consider the Earth firstly, well, F equals ma, well, the force, which is the weight here, is 735, equals mass, which is m, times the acceleration. Now, I'm not told either, actually. I am. I'm not told the acceleration explicitly, but what we do know is on Earth, I did briefly go over that when we looked at it in the last chapter. On Earth, the acceleration, because it's going down, is 9.8. Okay, so it's mass times g, or 9.8. Okay, so the mass is 735 over 9.8, which is 75 kilograms. Okay, so that's the mass. Now on the Moon, F equals ma. Now again, we're told on the Moon the weight is 120 newtons, so the force is 120, equals mass, which we now know is 75, times acceleration. Now the acceleration isn't going to be g here. Yes, it's going to be falling down, right? It's what's going on here is the astronauts essentially falling down, but the acceleration due to it falling down is at 9.8. It's only 9.8 on Earth. Okay, so it's going to be a different acceleration due to gravity. So to work out this, A is going to be 120 over 75, which is 1.6 meters per second. So there we are. So the acceleration due to gravity is different here on the moon compared to the Earth, okay? And you do need to sort of be aware of that fact. It is on the spec that if you're on planet Earth, the acceleration, which is 9.8 when you're falling down, is different to other planets or something like that. Although it's a very minor point, but there we are, and it makes sense here because the acceleration due to gravity is a lot smaller on the moon. Because if you think about it, the moon is like zero gravity. You really are just floating in space, so there's going to be less force, or you're going to be moving downwards, not as fast, okay? Because you're just hovering about. There's less force kind of keeping you down on the planet, okay? So there we are. Okay, okay, now let's have a look at, I guess, a more familiar question. Okay, so we're told here a force of 10 newtons acts upon a particle of mass 3 kilograms, causing it to accelerate to along a rough horizontal plane. So again, this horizontal plane is a horizontal. Don't get too bogged down in the wording. It's just a horizontal sort of line. So we're told this particle, again I'll just draw this little box to represent it, the mass is 3 kilograms, it's going to accelerate at 2, so the acceleration here, I assume it's going to go forwards, is 2 meters per second, and we're also told it's rough. Now you need to remember that a rough surface has friction, so if it's going to be moving forwards, there's going to be a friction force I'll call F, okay? And actually the force that's pulling it forwards, we're told is 10 newtons, okay? So there we are. Now there would also be weight pulling it down, that's going to be 3, so the mass, which is 3 times G, okay? Or remember, weight is mass times G. Now there will also be a reaction force. I'm not going to include it. I'll just call it R. We probably don't need to work it out. You probably will know it's going to be 3G though. But I'll leave it there. So that's all the forces. Now it wants me to calculate the force due to friction. So this friction here. Again, if we use F equals ma, well, firstly, if we resolve to the right, because that's where the acceleration is, it's being pulled to the right by this force here. So it's going to be 10 newtons. So the right force take away the left force of F. Okay, and then that's resultant. That's going to equal mass times acceleration. So the mass is 3 times the acceleration, which is 2. So simply we get 10 minus F is going to equal 6. So F is going to be 4 newtons. And I can say that here, 4. And there we are. Cool. Okay, now we've got this question here. So we're told here a trolley of mass 50 kilograms is pulled from rest in a straight line along a horizontal path by means of a horizontal rope attached to its end. The trolley accelerates at a constant rate. After 2 seconds, its speed is 1 meters per second. As it moves, the trolley experiences a resistance to motion of magnitude 20 newtons. Okay, so there's a lot going on here. So again, let's just plot the stuff we're given. So, firstly, horizontal. That again means it's just going to be a horizontal line like this, where the trolley is on. If we draw a trolley, just again a little block, the mass is 50, so 50 kilograms. Now it said it's being pulled by a horizontal rope to its front end, so it's going to be by the front. It's going to be a rope here, okay? So there's a rope in the front of the trolley, this force here, that pulls it along. Now, we don't know what that force is. Now, that's going to be a tension force because it's the rope, okay? The force in the rope, which is the tension, pulls the thing forward. So it's T for tension. Okay, what else are we told? we're told the trolley accelerates at a constant rate. We're not told anything, but we don't know exactly what the acceleration is. We just know it's acceleration. So I'll call it A, meters per second, okay? We also know some stuff about the time it takes to move. So we're told here, it says in 2 seconds, the speed is 1. Okay, so if we plot all that as well, we're told initially it's at rest. So initially it's 0 speed. After 1 second, so say if it's over here now, 2 seconds, the speed goes to 1. So now it's 1 meters per second here. And the time is 2. It wants me, and then it says, as it moves, the trolley experiences a resistance. So the resistance, if it's going to move forwards, the resistance, probably because of friction, acting the other way, we're told that force is 20. Okay, so I think that's everything we're given. Okay, a lot of stuff there. There we are. Hopefully you're with me with how I've labelled the diagram. Okay, what the parts were given. Right, so we've got this part. Okay, so this is what we got here. Initially we're told the velocity is 0. After 2 seconds it moves to 1 speed. The acceleration is A. I don't know what it is, but in part A they want me to work out the acceleration. Okay, so well, this is quite a complex problem because there's a lot of stuff going on. If we were to just use F equals ma, you can do that, that's fine. Well, the acceleration again is going to the right, okay, that's where the arrow's going. So to the right, if we resolve to the right, well, there's a tension force pulling it forward. Take away the resistance of 20. That's going to equal mass times acceleration. Well, the mass is 50, so 50 times the acceleration A. So therefore, we're going to get T minus 20 is 50A. Now you can see the problem here is I need to find T before I find A. I can't find the acceleration due to F equals ma. But what I'm going to use instead is, hopefully you realise what I can do with all this other information here. I'm told the initial speed and a final speed after 2 seconds. That again screams suvat. So if I do suvat then, if I do up here, well, S, my distance, I'm not giving anything about distance, I don't care about it. The initial velocity is 0. The final velocity is 1. The acceleration is what I want to work out, and T is 2 seconds. So I'm going to use the formula V is U plus AT. It doesn't include S. So then 1 is going to equal 0, add 2A. So therefore 2A is 1, A is 0.5 or half. Okay, so that's my acceleration. Okay, so that's just suvat for part A really. In part B then it wants me to find the tension. Well, I've already done kind of a lot of the work, right? Because I got T minus 20 is going to equal 50A. But we know that A, the acceleration was 0.5. So T minus 20 is 25. So therefore T is 20, add 25, which is 45 newtons. There. So that is my tension in the rope. This tension force here. 45 newtons there. And that 45 newtons again opposes the resistance of 20. Okay. Let's have a look at this though. So we're told a lift of mass 500 kilograms is lowered or raised by means of a metal cable attached to its top. The lift contains passengers whose total mass is 300 kilograms. The lift starts from rest and accelerates at a constant rate, reaching a speed of 3 meters per second after moving 5 meters. Okay, again, a lot of stuff going on, and again, it's talking about starting from rest. A speed of 3 meters after 3 meters per second after distance of 5. We're going to need to use suvat again, hence why suvat is here. Okay, but if I just draw the actual situation, so like the forces, I guess. Well, we're talking about a lift. So if I draw again a little box, Now a lift or an elevator, obviously it goes up and down. It goes up and down on floors. The mass is 500 kilograms. But in addition to the lift, pay attention to this. The lift contains passengers whose total mass is 300 kilograms. So what we've got is the lift has its own mass and the passengers add on mass themselves. So the total mass is not 500, but 500 add 300 to get 800. So that is the whole mass we're dealing with, okay? Now, we're told it's lowered or raised, so the lift goes up and down, right? Just like a normal lift, you know, in a building, and it's being raised by a cable. So a cable is attached to the lift like this, and there's going to be tension. Well, firstly, there's going to be weight as well. There's always going to be a weight that tries to pull the thing down. Well, the weight here acts downwards is mass times G. So the mass is 800, so it's 800 G. That's the weight pulling it down. Now, because it's connected by a cable, it's a sort of rope, there's going to be tension. Now, think about it. Because the whole elevator is going to want to try and pull the rope down, the tension will act the other way because it's been stretched. So the tension will try to oppose the stretching. So you got the elevator at the end of the cable pulling it down. So to oppose the stretching, the tension and the force will act the other way, and that's what keeps the elevator up. So to oppose the weight. Okay. Anyway, so that's the tension force acting upwards. So there we are. That's really all the forces actually. But there we are. So what's the acceleration in the lift? Now let's add on these other bits. So we said it starts from rest. So it's going to want to it's going to go down, I believe. It doesn't say, does it? It says it's lowered or raised, so it could go up or down. I don't know. I'll just assume it's going down, right? I guess it makes most sense. So the acceleration is going to go down, right? And also, we're told the initial speed or the velocity. Well, we're told it starts from rest. So initially, the speed is 0. And after it moves 5 meters, so I assume it's 5 meters downwards, right? After it moves 5 meters, say here, then the speed afterwards is 3 meters per second, okay? Now, if it was to use F equals ma here, again, it involves tension. There's an unknown force, T, the tension. So I can't work out A from that because there's there's another unknown. Well, we're going to use Suvat, okay? So again, Suvat, well, the distance we moved down by 5. U, the initial speed is 0. The final speed we're told is 3 after it travelled 5 meters. A, the acceleration is what we want to work out. So in part A, they want me to work out the acceleration, and T, I don't care about here. So the formula that does not involve T is V squared is U squared plus 2AS. So 3 squared is going to be 0. Add 2 lots of A, lots of 5. So that means we get 9 equals 10A. So therefore A is 9 over 10, or 0.9. There we are. So I can add that on. So the acceleration is 0.9 here. Now, a very important thing to note is because the elevator is moving down, you'd think maybe it'd be going down, the acceleration would be G. It'd be just 9.8 because it's falling down, right? We looked at examples in the last chapter where things move down vertically, so the acceleration was 9.8. No, because in this example there's an additional force, tension, that's pulling it up. If the only weight the only force is the weight, which then makes the object fall down. If the only force is the weight, then yes, it'd be 9.8. But because there's extra forces on, so we've got this tension force as well, the acceleration is not 9.8. It's not just falling down, okay? So, important thing to note there, okay? So the acceleration is not 9.8 here. As we can see, it's 0.9. So there we are. Then we want in part B, now it wants the tension in the cable. So here, the tension when the lift is moving vertically downwards. Okay, well, we kind of assumed it was going downwards. So let's work with this. So, part B, if it's moving downwards, so if we resolve then, right, so we're going to consider the forces. So if we resolve downwards, because it's moving down, well, the weight force is the thing going down, so 800G, take away the upwards force, which is tension. That has to equal mass times acceleration, right? So it's 800 for the mass times the acceleration of 0.9. Right, so in that case, if we then solve this equation, we get 800G. So it's going to be 800 times 9.8. Take away T is going to be 800 times 0.9, which is 720. Okay. And 800 times 9.8 is 7,840. Take away T is 720. Well, at that point, we could say that T is going to be 7,840. Take away 720 to get me T is 7,120 newtons there. Okay, then it's once in part C. Okay, the tension in the cable if the lift is moving vertically upwards. Right, so if it's now moving upwards instead, well, the forces will still stay the same. If it's moving upwards, again, the tension will still pull the elevator up, and the weight will still pull it down. The forces are fine where they are. But if it's going upwards, well, the acceleration needs to go the other way. Okay, so as does everything else. But actually, because we're using F equals ma, we don't care about the speed or the distance. We only care about the acceleration. So I'm just going to leave everything else where it is. I don't care about the speed or whatever here. But the acceleration has to change the other way because we're told it's moving upwards now. Okay, so if we do that, if we now resolve, well, if it's going upwards, let's resolve upwards now instead of downwards. Well, the upwards force is now T, and we're going to take away by the downwards force, which is the weight of 800G, equals mass times acceleration. So again, 800 times 0.9. Okay, so then T minus 800 lots of 0.9, lots of 9.8 for G is going to be 800 times 0.9, which is 720. So T is so then T take away 7,840 equals 720. So T equals 720 add 7,840, which is 8,560 newtons there. Okay, so you can see even just minor detail of just the acceleration going the other way can change your answer. So again, you do need to pay attention to where things move. Okay, if you can. But there we are. Okay. So hopefully it made sense. Again, quite a complicated question that is. But hopefully you're with me there. But there we are. Okay, so we got this question here. So here we're told the engine of a van of mass 400 kilograms. Again, I'm just going to jump to just plotting the information. So the van is on a horizontal road. So we have this road here. We have the van. We have the mass, which is 400 kilograms. What else do we know? In terms of forces, right? Well, in terms of forces, we're told the van comes to rest without the brakes being applied. Okay, in a model, the situation it is assumed that the van is subject to a resistive force which has constant magnitude 200. So again, if it's going to move forwards, the resistance is going to be 200 newtons. That's what we're told. So again, that could be due to friction or whatever else opposes it. But we're told now there is not going to be a driving force of something pulling it forward, because we're told the engine of the van cuts out. That means the engine's not working. That means there's no driving force, because that's what causes the car to move forward, or the van, is its engine. But the engine's not working, there is nothing pulling it forward, okay? And we're told the van comes to rest without the brakes being applied. So you can imagine it has some speed, right? So the initial speed was 16, okay? 16 meters per second. Then we're told it comes to rest. I don't know how long after, but it comes to rest, say over here, at some point down the road here. Now that makes sense, because if there is no force pulling it forward, that means it's going to have to slow down, because the only force we have is opposing it, right? It's opposing it going forward. So eventually this resistive force is going to slow it down if there is no forward force to pull it forward. Okay, that makes any sense? So that's the situation we've got. And I believe that's really all the information we've got. So it says in part A, find out how long it takes to stop. So it wants the time. Okay, so if I use suvat, then again that's going to involve suvat. Well, S is the distance. So the distance here for when it stops, I don't know what that is, and I don't care about it. U, well, the initial speed is 16. V, it goes to 0 speed finally, so it comes to rest, so that's when the V is 0. The acceleration, I don't know, but T is what I want to work out the time. Now I'm in a bit of a pickle, because I need to deal with 4 things. The only thing I've got at the moment is U, V, and I want to find T. I don't know S or A. You do need to know 3 things. I only know U and V. But I can work out A, can't I? I can work out A by using F equals ma, right? So again, it's going to accelerate A forwards. So if it's still moving forward, right? But you can think of it, the brake is slowing down, like the brakes are applied or something. No, sorry. There's no brakes, but it's been slowed down by the resistance, so the friction on the road. So the acceleration it's still moving forward, but it's slowing down. Anyway, until it comes to a stop. Okay, so if we use F equals ma here, so if we resolve to the right, as we assume it's moving to the right, well, the only force, well, there's no force to the right, the only force is to the left. So horizontally, we only got this left force, but because it's the opposite direction to the right, we make it negative 200. So essentially what we've got is there's 0 newtons, there's no right force, so we say 0, take away 200, the left force. So 0 take away 200, or just minus 200, equals mass times acceleration. The mass is 400 times the acceleration A. Well, we can work out A here, right? So A is minus 200 over 400, which is minus 0.5. So minus 0.5 here. Now, this makes perfect sense, right? You might be thinking, I've got a negative. What? But the negative, if the acceleration is negative, remember, negative acceleration just means it's slowing down, okay? It doesn't mean it's at negative speed or anything like that. It does make sense here, because acceleration, if it's negative, just means it's slowing down. But that's the exact situation we've got, right? It's slowing down because the only force is slowing it down. It's opposing it, right? So it makes sense to be negative here, okay? Right, okay, then part B. Oh no, sorry, we ain't done that. No, we need to find how long it takes the van to stop. My apologies. That's the acceleration, that's minus 0.5. Right? So if we then use SUVAT now, because now we know what U, V and A are, we can work out T. We can use V is U plus AT here, because it doesn't include S. So 0 is going to equal 16 minus 0.5 lots of T. So we get minus 16 is minus 0.5 T. So T is minus 16 divided by minus 0.5, which is going to be positive 32 seconds. So that's the time it takes for the van to stop. Okay. Right. Then in part B, it wants to find how far the van travels. So now it wants the distance. So we're going to use SUVAT. Well, we know the time is 32. So if we list our SUVAT, now S is the distance which we do want now. U is again 16. V is 0. The acceleration is minus 0.5. And T we worked out to be 32. So actually you can pick whatever formula you want as long as it includes S. Well, I'm just going to use S as UT at a half AT squared. So S is going to be 16 lots of 32 add a half lots of minus 0.5 of 32 all squared. And so that will get me 256, and that'd be in meters for distance there. So there we are, that's how far it takes to stop. Okay, now in part C it says comment on the suitability of the modelling assumption. So it says the model, it is assumed, so this is the assumption, that the van is subject to a resistive force of constant magnitude, so the constant amount of 200 newtons. So what's wrong with that sort of assumption? Is it suitable or not? Well, obviously it makes sense to be a resistive force, right? It makes sense to have friction or something like that. But the issue here with the assumption, so this whole sentence that I've underlined here, the main issue is constant. Forces and many things in life, especially in physics or mechanics related scenarios, not many things are constant. Speed, acceleration, all of that will vary. It will constantly change. Okay. Likewise, the force opposing it. The force opposing it, so the friction will always be 200 newtons. Think about it. A very, very, very slow car is not going to have the same friction opposing it as a very fast car at, like, I don't know, like 8 miles per hour. The friction is going to be different, right? So it doesn't make sense to be constant all the way through, no matter what. And also, the faster you are as well, you'll have even more resistance. So it's not suitable because, well, the assumption is not suitable. So the assumption that the resistance force is constant is not suitable. Okay. Obviously it's suitable that there is a resistive force. What's not appropriate is that it's always constant, the same throughout the journey, as the resistance would continuously vary throughout the journey. And I'd say in particular, there would be more resistance the faster you move, okay, the faster you travel, the faster your speed is. And so there we are. Okay, so there we are. We're going to finish with an exam question, which, to be honest, you'll probably breathe a sigh of relief compared to the questions we just seen. Okay, so we've got this diagram here. We're told a particle has mass 5 kilograms. You can see that here. The particle is pulled along a rough horizontal plane by a horizontal force of 28 newtons. Again, you can see that here. The force to the right is 28. The only resistance to motion is a frictional force of F newtons. They want me to work out the magnitude or the size of the normal reaction. So firstly, remember, there's weight that pulls it down. Well, what's the weight going to be? Mass times mass times g. So 5 lots of g. And so then the reaction force, I guess again is opposite the weight. It's a normal reaction. So again, it's perpendicular to the surface. Okay, so we've got this reaction upwards. So if we resolve upwards then, right, so upwards vertically, where we've got the reaction force, take away the downwards force of the weight, so take away 5g, and so then that equals, again, mass times acceleration. Well, the mass again is 5 kilograms, but the acceleration is, well, it's moving to the right, so the acceleration is acting to the right, but not vertically. So the acceleration only works horizontally. There's no vertical acceleration. It's not moving up or down. So it's 0. So we just get that, therefore, R equals 5g. So then R is 5 times 9.8, which is 49 newtons. Okay, and that's my reaction force there. Part B, the particle is accelerating at 1.4. So if I do an acceleration of 1.4 meters per second there, it wants me to work out F. So now I'm probably going to need to use F equals ma because I've got acceleration. So if I resolve to the right, so forwards, because that's where it's moving, to the right, well, the right force is 28 newtons. So 28 take away the left force, which is F. That's going to equal mass times acceleration. So mass is 5 times acceleration is what we want to work out, right? So A. So, oh no, we told it, sorry, it's 1.4. 1.4, there we are. So now we get the equation, 28 minus F. Well, 5 times 1.4 is 7. So F is going to be 21 newtons. So that's F there. Okay, so there we are. So that is it for this section. So again, hopefully you're comfortable with how we can apply F equals ma there. Okay, so there we are. I'll see you next time.